In this video, we are going to learn how to draw Lewis dot structures for molecular compounds. Molecular compounds are made from only nonmetal elements. In molecular compounds, electrons are shared between nonmetal atoms, forming covalent bonds. Covalent bonds are typically represented as lines rather than pairs of dots between atoms. In molecular compounds, atoms are not concerned with how many valence electrons they started with. Instead, they share electrons in whatever way is needed so that each atom ends up with 8 valence electrons. This is known as the octet rule. The octet rule comes from the fact that the s subshell can hold 2 electrons and the p subshell can hold 6 electrons. 2 plus 6 equals 8. There is an important exception to the octet rule. Hydrogen can only have a maximum of 2 electrons because it is in the first period of the periodic table, where there is only an s subshell and no p subshell. Most molecular compounds form small clusters of atoms surrounding a central atom rather than long chains. Before we begin drawing Lewis structures, let's review some important vocabulary. A pair of electrons located between two atoms is called a bonding pair. Bonding pairs may be shown as either a pair of dots or as a single line representing a covalent bond. A pair of electrons located on only one atom is called a lone pair. Lone pairs are not involved in bonding and belong only to one atom. Atoms located in the middle of a molecule are called central atoms. Some molecules may have more than one central atom. In most cases, the central atom is the more metallic element, which is usually written first in the chemical formula. However, hydrogen is never a central atom, because it can only form one bond and can hold a maximum of 2 electrons. Atoms bonded to the central atom are called terminal atoms. Terminal atoms are the ends of the molecule. You can remember this because the word terminal often refers to the end of something, like an airport terminal. For some simple molecules, you can almost play connect the dots to predict the bonding. Here we have 1 nitrogen atom and 3 hydrogen atoms. Nitrogen has 5 valence electrons, shown as 5 dots. Each hydrogen atom has 1 valence electron. Every unpaired electron can pair with another unpaired electron to form a covalent bond. The Lewis dot structure for ammonia has nitrogen in the center with 3 single bonds to 3 hydrogen atoms and 1 lone pair remaining on the nitrogen atom. Now let's look at another example. This molecule has 1 carbon atom, 1 oxygen atom, 1 fluorine atom, and 3 hydrogen atoms. Matching the unpaired electrons shows that carbon forms 4 single bonds. Carbon bonds to 2 hydrogen atoms, 1 fluorine, and 1 oxygen atom. The remaining hydrogen atom bonds to the oxygen atom. The completed Lewis dot structure has the bonding pairs typically shown as lines instead of pairs of dots. Sometimes atoms must share more than one pair of electrons to satisfy the octet rule. For example, 2 fluorine atoms each have 1 unpaired electron, so they share 1 pair of electrons to form a single bond. 2 oxygen atoms each have 2 unpaired electrons. To satisfy the octet rule, they share 2 pairs of electrons, forming a double bond, which is represented by 2 lines between the 2 atoms. 2 nitrogen atoms each have 3 unpaired electrons. They share 3 pairs of electrons, forming a triple bond, represented by 3 lines. When counting electrons around an atom, each atom counts all of the shared electrons in its covalent bonds as though they belong entirely to itself, even though the bonding electrons are shared between the 2 atoms. Each atom counts them when determining whether it has an octet. Although the connect the dots approach works well for many simple molecules, it does not explain the bonding in a general way. In reality, all of the valence electrons are shared throughout the entire molecule. You can think of this like a potluck party. Everyone brings food to the party, and everyone shares it. Likewise, each atom contributes its valence electrons, and those electrons are shared throughout the entire molecule. The only thing that each atom cares about is ending up with a full valence shell. Now let's learn a general procedure for drawing Lewis dot structures. This method works for any molecular compound as well as many polyatomic ions. Our example will be the nitrate ion, NO3 with a 1- charge. The first step is to determine the total number of valence electrons. Nitrogen contributes 5 valence electrons, and each oxygen atom contributes 6 valence electrons. There are 3 oxygen atoms. Finally, because the ion has a 1- charge, we add 1 additional electron. That gives us a total of 24 electrons that must appear in the Lewis structure. Next, we draw the molecular skeleton. Nitrogen is the center atom because it is listed first in the chemical formula. Arrange the 3 oxygen atoms around the nitrogen atom as terminal atoms. Next, connect each oxygen to the nitrogen with a single bond. This single bond contains 2 electrons. Since we have drawn 3 single bonds, we have used 6 electrons, leaving 18 electrons to place in the structure. Distribute the remaining electrons to the terminal atoms in pairs. Give each oxygen atom 3 lone pairs. That way it completes its octet. Remember that each lone pair contains 2 electrons. After doing this, all 24 electrons have been placed in the structure. Now, check whether each atom satisfies the octet rule. Each oxygen atom has 8 electrons around it, 2, 4, 6, 8, but the nitrogen only has 6, 2, 4, 6. We cannot simply add 2 more electrons because we have already used all 24 electrons that belong in the structure. Whenever there are not enough electrons for every atom to achieve an octet using only single bonds, we must create a double bond or a triple bond. Multiple bonds only form when there is an electron shortage. Always begin by drawing single bonds first. Nitrogen needs only 2 more electrons to complete its octet, so we will create 1 double bond. Choose 1 oxygen atom, erase one of its lone pairs, and then use those 2 electrons to form a double bond with the nitrogen. In the completed Lewis structure, nitrogen has 1 double bond to an oxygen atom and single bonds to the other 2 oxygen atoms. Each singly bonded oxygen has 3 lone pairs. The double bonded oxygen has 2 lone pairs. A helpful strategy when checking the octet rule is to focus on 1 atom at a time. Ignore the rest of the molecule and count only the electrons surrounding the atom you are examining. Finally, because the nitrate ion is a charged ion, place the entire Lewis structure inside of square brackets and write the 1- charge outside in the upper right-hand corner of the brackets. Let's do another example by drawing the Lewis dot structure for oxygen difluoride, OF2. The first step is to count the total number of valence electrons. Oxygen has 6 electrons and fluorine has 7 valence electrons. 6 plus 2 times 7 gives us a total of 20 valence electrons. Next, draw the skeletal structure. Oxygen will be the center atom, and the 2 fluorine atoms will be terminal atoms. The element written first in the chemical formula typically goes in the center. Draw single bonds between oxygen and each fluorine atom. Each covalent bond contains 2 shared electrons, so the 2 bonds use a total of 4 electrons. That leaves 16 electrons remaining. Now distribute the remaining electrons to the terminal atoms. Each fluorine needs 3 lone pairs to complete its octet. Adding 3 lone pairs to each fluorine uses 12 more electrons. Now we have 4 electrons left. Place those 4 electrons on the center oxygen atom as 2 lone pairs. Now, all 20 electrons have been used. Notice that every atom has a complete octet, so no double bonds or triple bonds are needed. The final structure has two single bonds with the oxygen atom having two lone pairs and each fluorine atom having three lone pairs. Now it's your turn to practice drawing Lewis dot structures for the following species: NCLO, CO3 2 negative, NO2 negative, H3PO4, SO3 2 negative, and CO2. Let's begin with NCLO. The total number of valence electrons is 18. Nitrogen contributes 5, chlorine contributes 7, and oxygen contributes 6. Place the nitrogen atom in the center and connect it with single bonds to the chlorine and oxygen. The two single bonds use 4 electrons, leaving 14 electrons. Distribute those electrons to the terminal atoms first, then place any remaining electrons on the nitrogen. At this point, nitrogen still does not have a complete octet. To satisfy the octet rule, convert one lone pair on the oxygen to a second bond between oxygen and nitrogen. The final structure has a double bond between nitrogen and oxygen and a single bond between nitrogen and chlorine. Nitrogen has one lone pair, oxygen has two lone pairs, and chlorine has three lone pairs. Next, let's consider the carbonate ion, CO3 2 negative. Count the total number of valence electrons. It's 24. Carbon contributes 4, and each oxygen contributes 6, for a total of 18. The 2 negative charge adds an additional 2 electrons. Place the carbon atom in the center and connect it with single bonds to the 3 oxygen atoms. The 3 bonds uses 6 electrons, leaving 18 electrons. Distribute those electrons to the oxygen atom until each oxygen atom has 3 lone pairs to complete their octet. Now the carbon atom does not have a complete octet. Convert one lone pair from the oxygen into a double bond with carbon. Because this is an ion, we will need to place the entire Lewis structure inside of square brackets and write the 2 negative charge outside of the brackets. Now let's draw the nitrite ion, NO2 negative. There are 18 electrons. Nitrogen is the center atom, with 2 oxygen atoms attached by single bonds. After distributing the electrons to the oxygen atoms, place the remaining electrons on the nitrogen. Nitrogen still does not have a complete octet. Convert one lone pair from one oxygen into a double bond with the nitrogen. The completed structure contains one nitrogen-oxygen double bond and one nitrogen-oxygen single bond. And the entire structure is enclosed in square brackets with a 1 negative charge. Next is phosphoric acid, H3PO4. Hydrogen is never a central atom. Place the phosphorus in the center. The oxygen atoms will connect to the phosphorus with single bonds, and the hydrogens will connect to the oxygens. There should be a total of 32 valence electrons in the structure. Distribute the remaining electrons to the oxygen atoms until they each have a complete octet. In this course, we do not draw any phosphorus-oxygen double bonds. This structure is complete using only single bonds. Now let's draw the sulfate ion, SO3 2 negative. There are 26 valence electrons. Place the oxygen in the center and connect it to the 3 oxygen atoms with single bonds. The 3 bonds use 6 electrons, leaving 20 electrons. Distribute the electrons to the oxygen atoms first, and place the remaining pair of electrons on the sulfur. Sulfur now has a complete octet, so no double bonds are needed. Since this is an ion, draw square brackets around the structure and include a 2 negative charge outside the brackets. Finally, let's draw carbon dioxide, CO2. There are 16 valence electrons. Place the carbon in the center and connect it to oxygen with single bonds. The 2 bonds use 4 electrons, leaving 12 electrons. Distribute the remaining electrons to the oxygen atoms. Carbon still does not have a complete octet. Convert 1 lone pair from each oxygen into a second bond with carbon. The final structure contains 2 carbon-oxygen double bonds, giving every atom a complete octet. The Lewis dot structures that we have been drawing are appropriate for this introductory chemistry course. However, I know that if you search the internet, you will find materials that go well beyond the scope of this class. I want to briefly mention a few topics that exist, but you are not responsible for them in this course. You are not responsible for learning about formal charge. You do not need to know how to calculate formal charges, and you do not need to minimize formal charges when drawing Lewis structures. You are also not going to be drawing Lewis structures for molecules that are exceptions to the octet rule. That means that we will not draw molecules with an odd number of electrons, molecules with expanded octets, or electron-deficient molecules like BH3. In this course, the maximum number of bonds around a center atom will be 4, since 4 bonds corresponds to 8 shared electrons to satisfy the octet rule. When we draw Lewis structures for nitrate, nitrite, carbonate, and similar polyatomic ions, you may have wondered how to decide which oxygen should form the double bond. The answer is, it doesn't matter. These molecules have resonance structures. Resonance structures are 2 or more valid Lewis structures for the same molecule or polyatomic ion. The atoms remain in the same positions, but the electrons are distributed differently. For example, sulfur dioxide, SO2, can be drawn with the double bond to the oxygen on the right or with the double bond to the oxygen on the left. Both structures are valid. The actual molecule is a resonance hybrid between these possible structures. Resonance hybrid does not mean that the double bond switches back and forth between the 2 oxygen atoms. Instead, the electrons are shared over the entire molecule. An analogy is a golden doodle. A golden doodle is a hybrid between a golden retriever and a poodle. It doesn't wake up one day as a golden retriever and the next day as a poodle. Every day, it's a golden doodle. Likewise, a resonance hybrid is always a blend between the possible resonance structures. The carbonate ion, CO3 2-, has 3 resonance structures. One of those structures is shown here. See if you can predict what the other 2 resonance structures would look like. Each resonance structure, the double bond appears between carbon and a different oxygen atom. But remember, the real carbonate ion is not switching back and forth between these structures. Instead, the actual structure is a resonance hybrid of all 3 possibilities.